Hi there, I'm lcnr. I'm currently the type stream co-lead and working on the Znext-solver. So, my talk is what, why, and when, so let's quickly do it. And this is what we're doing. The trait solver, it's checking whereabouts and it's normalizing stuff. And that's cool, we're already doing that. But we're gonna do it more. We will have new features, and we will also fix a bunch of edge cases, but still bugs are annoying, and there are even cases where Rust is unsound, where you use safe code, you get a seg fault. That's not good, so we're fixing it, even if those are very rare. And it will happen soon. So, first of all, why do you care? You might have seen input trait before. And in general, input trait can mean many things. The big ones are arguments and return types. And arguments are, from a type system perspective, really boring. They are just implicit generic parameters. So argument position, input trait, very nice implement, very pleasant, no bugs there. Return position is hard. Because for return position, we actually create an opaque type. We create some type where the compiler is responsible to figure out what goes there. Like, it's the compiler's job to infer the hidden type of an opaque. And also, like, depending on the context, you can either access the hidden type or you can't. So there's a lot of complexity with opaque types. And this is difficult to support properly with the old implementation. There are a lot of like subtle edge cases that don't work, bugs, things that shouldn't work but do. So yeah, and that's why we've spent a lot of time actually figuring out how opaques should work from scratch and then doing that in the new trait solver. And with this, we're then gonna solve this problem case. So here, we have a beautiful function. It returns an opaque type. It returns an input trait. But we want to store that input trait somewhere. We want to store it in a struct. And we just can't. And there's currently no way to name opaque types in Rust, which is annoying. And we want to change this. So ideally, with type alias input trait, you can name the opaque type, provide an explicit name for it. And then we can now store the type fib in a struct and use it wherever we want. And this is very powerful. It's mostly implemented since quite a few years, but because the underlying implementation of opaque types didn't work how we would want it to, it's blocked on getting the new trait solver ready. And we've also got return position, input trait, and traits, or async functions and traits. Those are already stable. But here we have an async function and traits. We want to use it in a generic context, and I call Tokyo spawn with it. This looks like something that should work. It does not. The problem is the async function and the trait. The only thing we know about that opaque type, or like that return type, it's not an opaque type. The only thing we know about that return type is that it's something that implements future. We don't know whether it's sent or not. And again, there's currently no way to name those things. But what if we could? So this is return type notation. And it gives you exactly that ability. You're able to somehow name async functions and traits or input trait, return position, input trait, and traits. So it gives you the way to name this. Now you can actually call Tokyo spawn in generic context, which apparently is a good thing. So yeah, this would be possible, but again, it allows you to name opaque types. So it encounters all the same issues, is blocked on the new trait solver. And there are also things that are not opaques. So you might have encountered this before. We've got some struct, we derive clone for it, and then we want to clone that struct. Do you think this works? It does not. And the problem here is that the derive we currently have in Rust, it just requires every generic parameter to implement the trait, which means that even though we've got like an RC, it's reference counted, it shouldn't have to be clone. The derive doesn't know this, so it just adds clone for the generic parameter anyways. and then trying to clone in a context where you don't know that this T is cloned, you get an error. Now, there already exists a crate and like design documents for what it could be instead. It's called perfect derive. You might have seen blog posts about it, you might have heard about it somewhere else. But the basic idea is that like this code works. You just took derive, replaced it with perfect derive, now it compiles. What we're doing is instead of requiring every generic parameter to implement the trait, we require that every field implements the trait. And this way, because our reference counted pointer doesn't require its value to be cloned itself, this doesn't require T to be cloned anymore. It works perfectly until it doesn't. So this is a list. A list either has a value, that's nice, or it has a pointer to an optional other list, like to the next list element. It's like the functional way to do lists. So that's a quote type. Let's use perfect derive again. Let's try to clone it. And it errors. And the reason this errors is actually kind of complex, so we'll get back to it later. OK, so we've got new features. We've also got bugs, especially around higher ranked things. I'm not sure how many people actually write code using like higher ranked lifetimes. So don't worry if like all that code looks a bit meh. Ideally, you shouldn't have to write this, but if you do, you probably shouldn't anyways because it's broken. So yeah, it works perfectly well. We have a generic function that for any it takes a reference of any lifetime and returns an owned value. We can use it like it has the same signature as clone. That's cool. What about this? It also has the same signature as clone, except that this time the argument is not a reference of any lifetimes. It is an associated type that like normalizes to a reference of any lifetime. Like this should just be a reference to any T again, but this time you get a type mismatch. So that's annoying. It doesn't work how it should. You might have encountered this. I know that like people working on Bevy, for example, encounter this a lot. So it always depends on what kind of code you write. And like that's annoying. It's something that should work, but shouldn't. We also have things that shouldn't work, but should. So this is beautiful code. I can try to explain it. That's a separate talk, though. So like we just use this beautiful main function, and what we get is a use after free. So yeah, that's like the code is very involved, and like that's good, because if there was code that you could hit by accident that is unsound, that's a big problem. If there is code you write like intentionally and that's unsound, still a big problem, but not as big. So yeah, we have a few of those. They are very hard to fix. We very much care about fixing them. You shouldn't hit them like on accident, but still we should fix them. And doing that also requires like bigger changes we can't just do in the existing implementation, but have to like need a bigger change upfront. So yeah, with those reasons, what are we actually doing in the trait solver? This is a very nice example. We have a function, it takes a vector, and it's trying to clone that vector. To do this, the compiler needs to prove that a vector of elements E is actually clonable. So we need to prove that a vec of E is clone. Now, how do we do this? We know that in the standard library, there is an impl that all vectors of type T implement clone as long as T is clone. So we can use this impl. And after using this impl, we now only need to prove the where clauses of that impl. So we need to prove that T is all vectors for all T implements clone as long as T is clone. We've got a vector of E, so we need to prove that E is clone. This time there is no impl, but we do have something else. We do have the where clause on the function. So again, we can use the where clause to prove this, and this time we're actually done. So that's the main job of the trait solver. You have a where clause, and it proves them recursively using most of the time either impls you've written manually or where clauses. So yes, that's the first half. The second half is another example, first of all. So here we iterate over a vector. And to do this, we can first desugar it a bit. So we create an iterator, then co-iterator next. Now, the type of element here, it should just be a reference to E. However, the compiler doesn't know it. The compiler only knows that the element is std slice iter of E as iterator item, which is nice, but like not helpful for you. So again, we like need to figure out what actually, like we need to figure out the underlying type. And we can use the impl again. So here, there's a beautiful impl iterator for iter of A and T. And that both tells us the item, which is a reference to T. And it could have nested where clauses again, which we would then have to prove. This time they aren't. So we're done, and we return that this associated type is actually a reference to T, and now we can use it however you want. So those are the two things the trait solver does. It proves where clauses, and it normalizes associated types. There's one thing we don't do, which is there are other where clauses, outlives clauses. So here, the trait outlives is only implemented for every type T that outlives A. And this is a where clause. The trait solver encounters those while proving things, but we don't do anything with them. We just return them, and then they are handled entirely separately. So anything to do with lifetimes or regions, which is how we call lifetimes internally sometimes, anything to do with those things is handled separately via borrow checking. That we've had one big change in the past in 2018 called LNL, and we are now currently, or people are now working on Polonius. And Polonius intends to improve our borrow checking to handle a few edge cases where we currently incorrectly error. But that is entirely separate from trait solving. So trait solving takes all the requirements and then hands them over to Polonius, or currently NLL, which then actually handles it for us. So that's nice, we don't have to worry about this part. Okay, so let's, with this knowledge, look back at the list example and what went wrong. So if we expand the perfect derive again, we see that it requires T to be cloned, and also the option box of list of T also has to be cloned. So let's look at what happens when proving that list of T is cloned. First, we need to prove that T is cloned, and the option box of list of T is cloned. T of clone is easy. We had a where clause again that T is cloned, so we're done. The option box of list uses an impl. So now we have to prove that box of list of T is clone. And now we have to prove that list of T is clone again. That's where we started. And those sort of cycles are sometimes fine, sometimes they aren't. Those things are called either co-inductive or inductive. And whether a cycle is one of the two is subtle, and getting it wrong is unsound. So yeah, we need to change a lot about the way we track this in the new trait solver. And well, we need to change a lot about how we track it, and the new trait solver does it better. So in the new trait solver, we should be able to handle this. In the old one, we're currently very conservative and error on most cycles, even though they should be fine. And like this is a case where the cycle should be fine, actually. Okay. So how did we end up with the trait solver? Well, it all started in the past. In 2015, we announced Rust 1.0 with a perfect type system, which is why 1 month later, we started working on Chalk. So Chalk was a separate project where we did an experimental trait solver for Rust, which was like a lot more focused on like what is actually the underlying logic we want. It was originally written in, was it data? In some other programming language, and like mostly focused on, okay, what is actually the right formalism we want for the type system, instead of like being the like performant replacement of what we currently have, at least not right away. So we've been working on Chalk, learning a lot about what should be the behavior, and while doing that, also like improving the existing implementation, which is how in 2019, we got async await, we got opaque types. They are stable, they use the old trait solver, and they work. The same with generic associated types. That's a pretty big type system feature we did using the old implementation. But also, like, as we kept on working on this, we realized like there are just issues we can't fix in one go. They require like a lot of interdependent things. It's very hard to do. So at the end of 2022, we also started working on a replacement of the trait solver to like get all those changes in one go. And we started working on this soon after. And in the middle of 2023, we now had the new trait solver be completely independent of the old implementation and like had the first working prototype. It was still a fairly long road from that, given that it's like 2 years ago. So another year later, we stabilized the Znext-solver in coherence checking, which is if you've got two impulses of the same trait, the compiler makes sure that those two impulses don't overlap. But like if there are types for which both impulses could be used, that results in unsoundness in Rust. So we don't allow this, and that checking is like quite self-contained. It doesn't use all the parts of the trait solver as much, so stabilizing it first worked very well. So we stabilized that in September, on the September 6th, and then we did it again because we broke Diesel. And this time it actually got to stable, which is very nice. That's what it should do. So yeah, you're now already all using the new trait solver. Every time you compile EuroRust programs, it's just in a small part of it. Something that happened recently is Rust Analyzer started using the next trait solver. It was using Chalk before then, and Chalk wasn't very maintained. It wasn't very fast from what I know. So Jacoid just did an amazing amount of work, like doing the initial enormous port, trying to change Rust Analyzer to use the next trait solver. So that landed in August. The people working on Rust Analyzer did so much more work, like getting it all ready. And they are apparently, from what I know, very, very close, as in like next week, that the first stable release of Rust Analyzer will use the new trait solver. All right, so that happened very recently. Let's talk about the status quo in Rust C. This is a benchmark testing type system chess, the most important Rust crate in existence, which checks whether your chess moves are valid using the type system. And here, we're more than 4 times as fast. So that is a very important crate. There are a few crates which are not quite as important, but still relevant. For those, we've got our internal benchmark suite, which in the Rust project, we just have a bunch of crates, and we can just test them and get very good benchmark numbers. And those aren't quite as pretty. So yeah, there's still a lot of work to do. It makes sense. Like the old trait solver has been developed for more than 10 years now. People have spent so much time optimizing it. And there are a bunch of low-hanging fruits, a bunch of slightly less low-hanging fruits. So I'm still confident that we will get there. But for now, the numbers aren't pretty. OK, so that's performance. We can also test whether we match the behavior of the old implementation. Because like, even if the new trait solver is better than the existing implementation, it doesn't matter if it breaks a lot of crates. So we've got a wonderful tool called Crater, which the project can use to just test all the crates on GitHub and all the crates on crates.io, and just like test whether a change breaks anything. And that then tests like 1 million different things and gives us results at the end. So there we are at roughly 1,000 right now, which are breaking. And that number is meaningless in itself. So let's actually look at the beautiful project board. It's so good. I love project boards. So a lot of the breakage is because we broke both Bevy and Mini Ginger. But that was intended. As in, they did things they shouldn't have. We sent them PRs which fixed it. They were very nice and actually accepted those. So yeah, there are now fixed versions of Bevy, fixed versions of Mini-Ginger that they are point releases, so there's no breakage if you update. But still, there are a lot of crates which have log files which depend on those. So with those, they are in the creator report. So even though it's 1,000 failing crates, a lot of those depended on Bevy. So the number isn't quite as bad. And the other remaining breakages are mostly, well, all the ones I know are comparatively easy. So they should take a few days, maybe a week to fix, which is nice because we had a few which took a year or half a year. So yeah, all the remaining issues should be fairly easy, and I expect that in the next few months to half a year, we're at a very, very good point and like ready for stabilization. Yes. Okay. So I didn't do this work alone. I also had a lot of work, a lot of help by Michael Goulet, compiler errors, who did so much stuff there, especially the more annoying work. A lot of that was done by him. And also, recently, I had Boxy review pretty much all my changes, without which it would have also not been possible. And outside of that initiative, there are also just so many more people like helped, either by like actually minimizing issues or doing smaller fixes, or just by providing the infrastructure. Like without Crater, this would have never been possible. So yeah, it's very cool. Thanks.